I did. It was like I thought it was like a day and a half. So like 25 hours to put 7 of them. Not like minutes, but like all day they sit the sun up and then the uninspected processes up the mountain. And I think it's like 7 days. Oh come on. Because only happens at night.
You ready to go, Juan?
I'm almost ready to go. Yeah. Yeah, I'm ready to go.
All right. Good morning, everybody. I hope everyone is recovered from our banquet last night. So the evening events are over, but Tassie is not yet done. We're happy to have Juan with his last lecture this morning.
Okay, so today we'll make a few somewhat disconnected remarks. The first topic will be some discussion of non-Gaussianities. So we discussed last time that the wave function of the universe is very close to Gaussian, and that's true. So now we'll discuss some aspects of the non-Gaussian corrections. Okay, this is the topic of the first part of this discussion. So been discussing cosmological correlators. So those are correlation functions which we can imagine. So we have some earlier inflationary period. So this is time going forwards. We have, and then we have the late universe, right? And we can think of this dividing line as a reheating surface. That's when we go from the inflationary universe to the hot Big Bang phase. And we can think of the later universe as complicated measurement apparatus that is measuring what's going on at the reheating surface. This is one way to think about it. Of course, what we really do is we are some observers who are late here, and we get signals from various points. And then we come up with a theory that there was a reheating surface, right? OK, good. Now, what we discussed in the previous lecture, we can think of that as computing some expectation value of two curvature fluctuations. So this is the fluctuation of the curvatures of the reheating surface. Okay. And we can now ask what the simplest correction would be a correction where we have a 3-point diagram. Maybe we have some bulk interaction. And now we compute a 3-point function. So that's the simplest non-Gaussian correction that we can imagine would be a 3-point function where there are 3 points. Okay. Now, one immediate question would be there are some issues that we can discuss about this. Well, first of all, where is this nonlinearity coming from? Well, we had the Einstein action and the scalar field action. So naively, you might think, oh, you might have a phi cube term in the scalar field action. And you might have such a term, but the slow roll condition will tell you that that term is very small. So that term is actually not very important. But you also have the nonlinearities in the Einstein equations. And that term turns out to be a little more important. And you have to, figure out what the effective vertex is for the physical degrees of freedom. And you get some 3-point bulk coupling. Now, you might also say, why couldn't we have also a correction in the initial state, right? So the initial state was some Gaussian state for the harmonic oscillators. But you could say, maybe you had also some non-Gaussian state as an initial state. And so naively, you might have two sources of 3-point functions. One is that the initial state might not be Gaussian, and the other is that there are some interactions later in the evolution that give you some non-Gaussian correction. Now, the idea is that when we do these computations, the state that we are choosing in the far past is not the adiabatic vacuum of the free theory. Should be the adiabatic vacuum of the interacting theory. Okay? And that's what really is choosing the state for us. And so really there isn't an independent choice of state and Hamiltonian and Lagrangian. So given a Lagrangian with its own nonlinearities, the idea is that that selects a state in the past, which is the adiabatic state for that Hamiltonian with those interactions. Okay. In the analogy with the harmonic oscillators, we would have an anharmonic oscillator, and we have to pick the vacuum of that anharmonic oscillator, okay, in the very early times. Now, this might sound like an abstract discussion, but when you go and actually do the computations, you will find that if this is eta conformal time, right? So this is the end of inflation, and this is the beginning. Okay, you'll have to evaluate some Feynman diagrams, and you'll have to integrate over this interaction vertex. You'll find some oscillatory features here in the past, and the idea is that the technical way to implement what I just was describing is that you deform this contour a bit in the imaginary direction. So this is the real part of eta, and this is the imaginary part of eta. And so you deform it a bit in the imaginary direction, and that selects the vacuum for you. And that is a prescription that works including the interaction. So when you do that, then these oscillatory pieces decay. This is chosen so that those pieces decay. And then we get a well-defined vacuum. Well, we get a well-defined answer for the computation. Okay. So the message of these last few remarks is no independent vacuum and Lagrangian. Lagrangian determines the vacuum. Now, point about the size of these interactions. Well, the effective coupling in this whole discussion is basically, well, first of all, this is an interaction vertex in gravity, so square root of g Newton. But really is square root of g Newton, which goes like h. So the dimensionless, once we put in the radius of the zeta and so on, this is something of order h over m Planck. Okay, so this whole so in the inflationary context, we have g Newton. G Newton is of course dimensionful, and we make a dimensionless combination with the radius of the zeta, right? So what we care is how big the radius of the zeta is compared to g Newton, or more precisely the opposite. So this is basically L Planck over the radius of the zeta. During the radius during inflation. And that's what governs how weakly coupled the theory is. Okay? Remember, the size of fluctuations were of this order, were also of this order. And so this implies the 3-point function divided by the 2-point function to the 3/2 will be of this order, h over m Planck, right? And then there might be some factors of epsilon. And when you do the calculation, there is indeed some factor of epsilon, which further suppresses it. Now, for historical reasons, if you look at how people normally quote these 3-point functions, they typically divide not by the 3-point function, but by the 2-point function to the 3/2, but the 2-point function to the squared. Right? I mean, the 3/2 is the natural units you would divide in the Gaussian. You had some original Gaussian. With the 3-point function has particular patterns, so there's some dependence on the 3 positions, or usually it's quoted in the momentum space, so some dependence on the 3 momenta. And different interactions might give you different patterns for these 3 things. So people look for these various patterns in the CMB, and they haven't found any. And they define some quantities, which is called FNL, which is the size of one of these patterns when you define it in this way. And the current bounds, so the inflation predicts, so the simplest theory of inflation with one field predicts this of order epsilon, so rather small. And the current bounds are that FNL is for one of the shapes is 5, and for other shapes it's about 40. So this roughly tells you, I'm quoting this because, well, this is some experimental, and I'm not telling you exactly how it's defined, so you should think about the relative ratios of these things. So we're very far from being able to test the non-Gaussianities that are predicted by the theory. That's message number one. You can search for other patterns which are not produced by the simplest model, but are produced by other models. So an example of a model that produces larger non-Gaussianities would be a model where the kinetic term for the field is more complicated. For example, instead of having d phi squared, you have, for example, square root of 1 minus d phi squared, and this is close to 1. So more complicated model. So these ones can produce more non-Gaussianity, and in fact, even bigger than this 5 that we have here. And so we have some constraints on these models from non-Gaussianity. In fact, an invariant way to say it is that in this type of models, the speed of sound of the scalar fluctuations is not the speed of light as it was in the simplest model, where we had a massless field in the sitter. But because of this non-trivial kinetic term and the fact that the derivative of phi in this model it would be perhaps close to 1, then the speed of sound becomes smaller than the speed of light. And so using non-Gaussianity, you can bound what the speed of sound should be. Then the bound is that so the speed of sound should be greater than about 1/12. Okay. Okay. So if it is if it is smaller, then non-Gaussianity would rule that out. So yeah. So non-Gaussianity is helpful for ruling out some models, and okay. So well, some points. So some points are already made. Let me summarize them. Non-Gaussianity is very small in the simplest model. You can ask, can we do better and perhaps in the future measure this? There is this problem that we discussed last time that we have only one universe and we are limited in the statistical power of some measurements in general. And so if you look at the total amount of information available just in the CMB observables, you cannot do this. So this is like maybe as good as you could do. However, there might be some other ways of getting at the primordial perturbations from some other observables that are more sensitive to the 3D structure of the perturbations. So CMB gives you a map which is essentially two-dimensional because it's it's a snapshot at some moment in time. And so you see basically what the primordial fluctuations were in a certain sphere. And so there are some ideas for getting at more 3D map, but these are more into the future. They involve 21 centimeter signals, etc. If you heard about this. But those in principle contain enough information to get to this. But we don't know whether that signal is there and whether there are some foregrounds. There are some foregrounds that are much bigger, so it's not clear we'll ever see them. Now, another interesting thing is that you could, in principle, non-Gaussianities could also give you information about some other particles that were present. So let me denote them like this. There could be other particles that were present during inflation, and this is, let's say, some interaction with the inflationary background. So imagine that another particle existed during inflation, then you would expect that that particle could decay to the inflatons. So those are these three vertices. And then, well, the inflaton has some non-trivial background, so that is one of the vertices absorbed by the background. So you get this type of diagram. So you would get a signal from an extra particle that was present during inflation. And that leaves a signature in the pattern of primordial perturbations. So it's an interesting, at the very least, it's an interesting theoretical problem to figure out what these possible patterns are and try to understand how you would see them in the CMB, or see them in the fluctuations, what's the best way to see them. So I think this is fun, and you can call this a cosmological collider problem, where you had some collision between particles during the inflationary period, and those collisions then leave an imprint in the primordial fluctuations. Okay. Now, in a sense, there is some analogy with the physics of colliders, some conceptual analogy in the sense that if you look at the pictures that you see coming into the building, right, there's a picture of a particle detector in the stairwell that is basically what's happening in the LHC. So some collision at very short distances, some first QCD physics, which is nearly scale invariant. That's similar to the physics of inflation, that we have some scale invariance. And then there is some hadronization, so some transition to a non-scale invariant, a different type of behavior. In inflation, we have that transition to reheating and then some further physics in the future. Finally, in that picture, you see the various jets at the detector surface, right? In inflation, these various jets would be the galaxies, right? You have various galaxies at different locations. And from those locations of galaxies, you're trying to figure out what happened in the early universe, okay? In the same way that from the physics of where those jets are deposited in the detector, we can figure out what happened in the collision in the QCD case. Okay, very good. So something fun to think about, and a unity of various physics. It's interesting how the same symmetries are governing these various different physical processes. But it's, again, the physics of slightly broken conformal symmetry in both cases. Okay, very good. I think I'll leave now the topic of non-Gaussianities, and so are there any questions people have about this?
Do most people just do this as like model building? You try to figure out a model, see what constraints you get from observations, or is there like a more first principle way people have been thinking about what should be the model in inflation, during inflation?
Well, yeah, so phenomenologically, you would like to be able to detect these other particles that could have existed during inflation. The leading signal might be just a contribution to the 4-point function, local contribution, when this particle, let's say, is very off-shelf. Yeah, so if you had some other particles that were very light, they could give some very important signal. It depends on what the size of this is. If this coupling is very large, you might worry that there are some constraints, like this coupling cannot be too large, otherwise you will get a correction to the potential, right? And so the potential has to be flat, so that gives some constraint on the couplings. But you still have some leeway that you could see them, and so you can, by doing observations, you can put bounds on the couplings. So people compute these patterns, and then they compare them to the data and put bounds on these couplings, on the masses and possible particles. Yeah. You can even put bounds on the possible spins of the particles. I'm not sure if this was done compared to the data, but at least in theory, these patterns also depend on the spin, on the mass and the spin of these particles. So I don't know. If we want to speculate, we can say, well, maybe in the early universe, this happened during a stringy phase where the string size was comparable to the Hubble scale. We don't have a concrete model of that kind, but you could see it in some pattern. That could, in principle, be there. But the problem is arguing that these couplings are big enough. So, I mean, the estimate of this type of diagrams is, again, the same type of H over M Planck that governs everything. So you would need to have different scales and some reason why this coupling is boosted a bit bigger than you might have expected. So H over M Planck is like the minimal size of these couplings. And these are also further suppressed by, so something important is what's the mass of these particles relative to the Hubble scale, right? So you would need to have some other particles of the same order as the Hubble scale. And then this gives you, you can ask, well, is it natural to have particles of the same mass, or maybe it's not so natural, and so on. So those are questions you can ask. I mean, in multi-field inflation model, you naturally have some other particles which are of these masses. Yeah.
Should we expect to see non-Gaussianities in like next 20 years, or is it small?
Well, yeah, sorry. The question is whether we expect to see non-Gaussianities in the next 20 years. Well, it depends on the model. So when that question was asked maybe 10 years ago, you could have said there are models like such a model, and that was one of the motivations for these models, that could give you large non-Gaussianities. So there were models that give you large non-Gaussianities. You could say, and it was said at the past, that these models are somewhat artificial. So probably you will not see. So if I had to bet at that time, I was betting against seeing this type of effects. And then there are sort of multi-field models where perhaps the decay rate of the inflaton is mediated by some other field and so on, also tend to give non-Gaussianities of order 1. Again, well, that's not so clear. We'll do much better. Now, there are some ways of thinking about non-Gaussianity by looking at the large-scale structure, and there's been progress in this direction. And so we expect to be able to shrink this from 5 to perhaps of order 1. So there might be some hint of a signal. Just to get to something smaller like this, you need this 21 centimeter tomography, which is detecting a certain, I won't discuss the details, but some other observation that does not involve the CMB. But the backgrounds for this signal are like 10 to the 4, 10 to the 8, I don't know. So the backgrounds are much bigger than the signal, so it's a big technological problem. Yeah, you have to be lucky to be able to extract that cosmological signal. Okay, any other question? And I should say that there is some activity in trying to understand the analytic structures of these correlators, and similar to the efforts trying to understand the structure of amplitudes, right? Of amplitudes and trying to figure out maybe alternative ways of computing it. And the interest, one motivation for that might be phenomenological, but another motivation is to try to see whether we have an alternative understanding for how to do this computation, which does not perhaps involve the bulk, and it's based purely on some bootstrap ideas. I mean, just thinking about the symmetries of the problem and figuring out what the possible singularities are and so on. Perhaps, well, maybe one extra point just to connect to some other things we said before is that there are some limits of this amplitude. So for example, when this point is very separated from these other 2 points, right? It's a bit like an OPE limit, operator product expansion. And the behavior of the amplitude in that regime is governed by the masses of these particles, or the same, which appear through some. So the structure of that OPE is similar to the structure of an OPE in a conformal field theory, and it's governed by some operator dimensions, which are the H plus minus that we discussed in the first or second lecture. And more generally, they are governed by the quasi-normal modes in the zeta space. So these are the same things. These operator dimensions that appear here are the same as looking at the spectrum of quasi-normal modes. So if we look at these correlators in the so-called squeeze limit, where 2 are closer than the other 2, than the third, we get some information about the quasi-normal mode spectrum of the theory during the de Sitter time. And that, of course, tells us what the particles are. And we could have 2 particle exchanges, for example. That gives something else, and so on. OK. Maybe we'll leave that topic now. And OK, what was I planning to discuss now? OK, some questions around inflation. OK, so this we'll get into. What questions do we? So last lecture was inflation is great, right? There are very predictive and wonderful physics from the 80s. So what will be the physics from 2025? The physics that some of you will discover, right? So we'll try to discuss some questions about inflation. So well, there is one question, which is whether inflation really happened. Maybe there is an alternative theory. So that's one possibility. But even if you grant inflation, there are questions like what happened before inflation? How did we get to that inflationary initial conditions? So So inflation works very well. There is some initial assumption that you had a little patch where the universe was relatively uniform within a patch of size h during the inflationary time. That can give rise to our universe. So that's perfectly wonderful. But how did we get to that initial conditions? Then the question of where the V of phi comes from, right? Of trying to understand inflation model building. So we can think of that in the effective field theory, or we can think of that from the point of view of string theory, which models are natural in string theory. So you saw in Liam's lectures how difficult it was to get the de Sitter vacuum in string theory, and by similar techniques, maybe he already discussed that, you could get inflationary models, and you could wonder whether, where those inflationary models that you get from string theory sit within the phenomenological ones, right? Are they special? Do they predict large amounts of gravity waves or small amount of gravity waves? Now, some of the inflation models you construct using the techniques that Liam discussed, especially in that particular context, they tend to have a small amount of gravity waves. So some amount that will not be detected in the near future. So if that's the generic prediction from string theory, then you have a falsifiable prediction. But unfortunately, people say, well, or fortunately perhaps, people say, well, maybe there are some other models which predict large amounts of gravity waves. They are less under control, but maybe. So we don't really know. We don't have a concrete prediction from string theory. That I think is one of the perhaps most interesting aspects where these ideas of swampland that people are exploring would be particularly interesting. So if you could say whether an effective field theory that predicts large amount of gravity waves is possible or not possible in quantum gravity. Okay. And hopefully we'll do that before, in the next few years, people are going to be ruling out certain amounts of gravity waves. So there is that parameter R, which is the ratio, or epsilon. They're going to be put in bounds that are stricter and stricter on epsilon. Okay. So that's an interesting question. Okay. So now let's discuss a little bit of what could have happened before. Okay. Yeah.
When people consider these models in string theory, do they consider fine-tuned initial conditions or generic? What kinds of initial conditions are you allowed to consider when seeing your?
Yeah. Let's discuss that a little bit. So when you are trying to model, when you're having inflationary models, let me discuss this in a qualitative way. So we discussed that we need a region of the potential like this, right? But if the potential before this region was perhaps too steep, so you could start here, and then when you come down, you might come down through this region too quickly, and you might not have inflation. So that's one failure mode, okay? Or you could have created a universe which has so many homogeneities that you can't find an inflationary patch. So that it's another potential failure mechanism. People have done simulations where they start with the universe here, but with lots of homogeneities. And the idea is that by random chance, there will be a place where the homogeneities are small enough that little piece will inflate, right? So you could imagine starting with lots of homogeneous. There happens to be, by chance, some place where this homogeneous over a scale of order h. Let's say this is the size of h. And so you can evolve this universe, and so most of these places might end up in singularities, right? But this piece will expand into the universe we would want. Okay. This is basically I would call it the Linde picture that proposed by Andrei Linde in the 80s. That you start with some random chaotic initial conditions, and there will be, by chance, some place where you are up enough the potential and smooth enough so that you can inflate. Okay. But still, you can ask, why do we have these initial conditions? And if you have the point of view of what happened, so the universe in the far future, let's say now, right? Now, the state of the universe today is a state of, let's say, relatively low entropy compared to what naively could have been. It could have been more inhomogeneous. It could have been an empty de Sitter. Depends on how you think about the entropies. But in most ways of thinking about it, it's a state of low entropy. And so from that point of view, this is a special initial condition. If you take the point of view that you set the initial conditions down here in the Linde way, then it's not so special. So depending on how you think about it, you might think it's special or not special. And understanding what's the right way of thinking about it is part of the problem. Okay. Very good. So I'd like now to discuss a phenomenon that happens in potentials like the one we were discussing before. So you have a potential like this, V of phi, and this is phi over m Planck. So let's say this is just 1. And we discussed last time that we can have slow roll inflation as long as phi over m Planck is bigger than 1, right? So then the slower conditions will be obeyed. And so there will be a regime here where we can have slow roll inflation. And then there is something interesting that happens. So if you look at the 2-point function for fluctuations, we discussed that it was equal to h squared over m Planck, right? That was one of the factors, and the other factor had to do with the slow roll parameter, which was h squared over phi dot squared, right? And this was small for the models we discussed, but if we go, in fact, so this is small in this regime, but if we go far enough up this potential, it could become large, right? So this factor is 1 over epsilon, right? So this factor is basically the potential in Planck units, which we always want to be small, right? At some point, if we go far up in this potential, that will fail, right? So this is, let's say here, we cannot talk about inflation anymore. That's when V is of order m Planck to the 4th, okay? Or h over m Planck would be 1, okay? That's this regime. But then this is a separate parameter that has to do with the phi over m Planck. And as we move up this potential, epsilon becomes smaller and smaller. So here epsilon is 1, and as we go up here, it becomes smaller and smaller. And it could, in principle, become so small that it cancels that. So when epsilon is very small, we have the ratio of 2 small things. This is one small thing. Epsilon is the other small thing. And this could become of order 1. Okay. And when you work through this for these power law potentials, that happens earlier than we get to this Planck scale. So it happens, let's say, around here. So in this whole regime, we have that these fluctuations are of order 1. Now, what does that mean? That means that the universe that will produce after the end of inflation would be very, very inhomogeneous. Okay? And typically, in such universes, you will produce black holes, which are, lots of black holes of the size of Hubble during the end of inflation. So it's not the universe we see. But there is some interesting physics about this, which is the following. So in this regime, what happens is the following. So what happens in inflation is the following. So if you ask what happens during an E-fold, so the field is rolling on the potential. And during an E-fold, so d phi dn, right? So that's phi dot over h, right? So that's how much the field changes in an E-fold. So when the universe is multiplied by a factor of E. And then this is one of the things that is happening. And the other thing that is happening is that the field is undergoing these random fluctuations of size of order h, right? Due to the quantum physics or thermal physics of de Sitter. Okay? And that's what was captured by that Starobinsky equation that we discussed in one of the lectures. But well, it's also a feature of the full quantum computation that we discussed. And so something interesting happens when this change in the field in one E-fold is of order h, okay, or smaller than h, right? In that case, in the whole universe, because of the first effect, right, the value of the field is decreasing, but because of the second effect, the field is kicked up or down the potential. So there will be, if we go from one Hubble size region after expansion E, we have 3 different Hubble size regions, right? And in one of them, the field might have gone up, right? A net value of up, because H might be bigger than this drift. In some other places, maybe didn't change. In some other places, maybe it goes down. In average, it's going down, okay? So maybe it goes down a little bit, okay? But as long as it's a place where it goes up, the universe will continue inflating. So this piece will again decay, and so on. There will be always some patch where it continues increasing. And if this is smaller, okay, there will be several patches with this increase. So this will lead to eternal inflation. So you start, the universe starts inflating, and somewhere it will continue inflating, and so on. So this regime is called slow roll eternal inflation. So this is slow roll normal inflation, and this is slow roll eternal inflation. Okay, so what this does is that if you try to look at the reheating surface in the regime in white there, so the usual slow roll eternal inflation. So the reheating surface is some surface which has some small fluctuations, right? For our particular universe of order 10 to the minus 5 curvature fluctuations. In this slow roll regime, we would have very large fluctuations and some regions where the universe really continues inflating, so where we haven't yet decayed, okay? So in every place, eventually will decay, but might be sooner or later. Okay. Now, if we had a potential like this, then maybe if inflation continued far into the past, then our universe at very long distances would have this shape, right? But we are observing it at shorter distances where it's a little bit more uniform, like here where the fluctuations are not so large. Okay? So if that regime was in the past, then the universe at very long distances would be very inhomogeneous. So that's one thing that could have happened. Now, in this regime, it's a little confusing how exactly we should compute probabilities. Well, maybe I'll first discuss, before I discuss a little bit the measure problem, I'll discuss one more thing. Well, I'll make, yeah, maybe, what time is it? Yeah, maybe I won't discuss that. Now, another regime you could have is you could imagine a potential where that has several minima, right? Okay. So in a situation like this, if you start here, you'll have a de Sitter space. Here you have another de Sitter space, and so on, with different cosmological constants, right? And in principle, if you started here, you could tunnel to here, right? So in that situation, the universe would look roughly like, we'll discuss the tunnel event a little in more detail later, but it would basically look like this. So we have, let's say, vacuum number 1 everywhere outside, and with some small probability, we create vacuum number 2, okay? So that's one possible decay. And in this case, it's somewhat analogous to that. These two regimes are conceptually at least connected, right? They are in detail different, but conceptually connected in the sense that here there will always be some place where we continue inflating in vacuum number 1, right? But eventually everywhere will eventually decay to vacuum number 2, right? Which is slower energy. And so we'll have a complicated fractal structure that you probably... Is this material familiar to everyone? Or? No. Yeah, so we have this. And now here, let's say we are in vacuum number 2, right? The universe, let's say, started in vacuum number 2. Then it is also possible to fluctuate up to vacuum number 1. I'll discuss in detail how to compute those rates. So in principle, we can also fluctuate to vacuum number 1 because this is a bit like system at finite temperature. So this is a universe that is at finite temperature, and when you're at finite temperature, it's always possible to have, let's say, a thermal fluctuation that fluctuates up. This is the intuitive understanding. So even if we start in vacuum number 2, we can also tunnel up to vacuum number 1. So here, we could also have some other bubbles of vacuum number 1 again, okay? So all these processes of tunneling between different vacua will tell us that if we start with one of them, we'll eventually sort of people call this populate the various vacua, right? So, so this is a mechanism, this mechanism of eternal inflation. So this is called bubble nucleation, eternal inflation. I'll explain the name a little later. But these tunneling processes tell us that if we start inflating in one of the vacua, we populate all the other vacua. Right? So it's a mechanism for accessing all regions of this landscape. In particular, it could be that, so a nice picture for what could have happened before our inflationary period is that there is some region in the landscape that contains our vacuum, okay? The landscape is very complicated, so it has very other regions that contain other vacua, right? This is a plot of the potential, which is multidimensional, right? Many other vacua, maybe in the other vacua, there is no standard model, there are maybe no possibilities of complex life, etc., right? But let's say this vacuum is anthropically possible. So in this vacuum, we have the standard model and a small cosmological constant, right? So it's a good one. Then we still need to create our universe. So we need this vacuum, and we need at least some region where it has the inflationary potential, right? So what could take us up at this point? Well, the potential might maybe have some feature roughly like this, where there is a metastable vacuum here that can then tunnel to some place nearby, and then from there we will have the slow roll eternal inflation that will produce the universe we would want. Okay, so that's I would say one nice picture. The advantage of this whole set of ideas is that, first of all, in string theory, let's say we have a complicated landscape. So in any theory that has a complicated landscape, you would not have to worry about where you start. So you can start anywhere, and then this eternal inflation process, as long as you started inflating, will eventually produce this universe with some non-zero probability. Okay. Now, this does not tell you that, let's say, it's probable to be here, more probable than to be in some other place. And you have to understand this question of the measure of how to now compute probabilities in this type of setup. Okay. And I would say that when you start thinking about this, it gets very confusing to decide. There is no universally accepted prescription for how to compute probabilities in this setup. This is called the measure problem in eternal inflation. Okay, I'll discuss now a little bit more in detail these tunneling processes and how we think about them, how we compute them. Okay, maybe we'll start with a simple quantum mechanical problem. Is the problem of understanding vacuum decay familiar to people or not familiar? Okay, well, discuss it. Starting from, let's say, in quantum mechanics, we can have a potential that let's say looks like we have some particle that starts here, right? Then there is a solution in Euclidean space which describes a particle that tunnels here, right? So it's a solution that as a function of Euclidean time, right? And now this is x. So this was x, and this was the potential v of x. So there is point number 1 and point number 2, right? So x starts at point number 1, right? And then it has some excursion to point number 2, okay? And so on. So you can believe that you could solve the classical equations. So in Euclidean space, the equations are for an inverted potential. So you can solve these equations, and this will be the behavior. And the idea is that the action, so the classical action of this trajectory, this is called the bounce trajectory. This gives us the decay rate for this process, okay, the decay probability for this process. So roughly speaking, what's happening is that this Euclidean evolution gives you the wave function at this point. You take the square, that's the probability, and that gives you the full evolution. And that action using WKB approximation is equal to this expression, and that's gamma. Okay. Okay, good. So that's that. Now, then you can ask, well, what about exactly the same problem in quantum field theory? Let's say in some quantum field theory. So in that case, the analog of this trajectory is a trajectory where we have vacuum number 1. So this was vacuum number 1 everywhere. Localized solution has a spherical shape. Okay. So we have vacuum number everywhere. We have a spherical solution with this shape. And the spherical, so this is in RD. So we have a d-dimensional Euclidean d dimensions to describe a theory in Lorentzian d dimensions. And in the same way that here you can, so the tunneling process goes in Euclidean time to here, and then we have a Lorentzian solution where the particle moves away and falls through this potential. Right? Here is somewhat similar. So we can cut this diagram at t equal to 0, right? And view this as creating a little bubble of where the field is interpolated between vacuum number 1 and some place. So here the equations are a bit different, and I think you will be somewhere else along this potential. Okay, there is a kind of friction term due to the radial evolution, and so it'll deposit you somewhere along this potential. Okay, and in the Lorentzian picture, so you have, let's say, the T Euclidean. Okay, the Euclidean picture, we have this bubble, and in the Lorentzian picture, this bubble really starts accelerating away, eating away the vacuum number 1. And here the field initially got deposited, let's say, at some point, let me call it 2' here, 2', and then it continues falling down as at r equal to 0. But the whole solution, here has a spherical symmetry, and here it has an SO1 d or d minus 1 symmetry that is inherited. So there are hyperbolic slices here with where the field is constant, right? So here the field is constant on spherical slices, right? Here is constant on, let's say, the Sitter slices, and here on hyperbolic slices. Okay. So that's the picture in quantum field theory. Now we consider the same problem in gravity. And so in gravity, we will start, so vacuum number 1 is a sphere, right? In Euclidean space, it would be a sphere. So we're trying to consider something analogous to this picture, right? So vacuum number 1 now will be a sphere. Vacuum number 2 would be, if we're tunneling between 2 minima, would be some other sphere in principle. But let's consider something more similar to that picture. So in that case, what we could have is a situation where we have some kind of solution, right? So there will be some solution in this region where the field goes from being 1 to being, let's say, around, let's say here it has some value 2', right, at the center of this bubble. So it will be a solution that roughly will have this topology. And we'll interpret this solution as saying, well, the exterior will be what we were drawing before, so some de Sitter space, right? So we have some de Sitter space in vacuum number 1. Well, we could think of that in Euclidean. So we have the half sphere of vacuum number 1, that is filled, so we're cutting this sphere roughly in this way, that is, we have the solution where the field is displaced. And then when we go to Lorentzian signature, this will give us the usual de Sitter in vacuum number 1. And we have some region where the field is displaced from the minimum of field number 1. And this deposits the field in position 2 prime. And here again, you have these hyperbolic slices. And the field will start rolling down with these hyperbolic slice symmetries. We'll start rolling down the potential. And eventually, if the potential has this flat region, it will start inflating, right? So if this was 1 and this was 2 prime, so the potential will start, well, the field initially, well, we have some negative curvature for the universe. So those are the slices where the field is constant, right? So the slices in the gauge where the field is constant and the curvature of the universe is negative in average. As we start inflating, the local value of the curvature will become smaller and smaller, right? Inflation will sort of flatten the universe. And if we have much more than 60 folds of inflation, we will not be able to see. The universe will become flat, right, as we see. Now, you can ask, well, how fine-tuned, well, you can ask, do we have any chance of seeing this negative curvature? So if we actually go and measure negative curvature in our universe, it would be some evidence for this, this last bubble nucleation process before our universe began. Okay, so that's something interesting that could, eventually we might be able to see negative curvature or some evidence of that, and that would be evidence in favor of this picture. Okay. So far, we haven't seen any curvature. So we have some bounds on curvature, which are, I don't remember the precise number, but it's around, I think, 10 to the minus 3. Okay, so this is how small the curvature is. So omega k. Okay, good. Okay, so this is one of the frontiers, eternal inflation and understanding how to think about the problem in this complicated landscapes. Also, there are landscapes. So if the landscape is like this, where there is an absolute minimum, there is an interesting probability distribution that you could discuss, which is the Huddle-Hawking one. Which says that P of phi is essentially e to the 1 over v of phi with a positive coefficient here. So as long as v is positive, then this does not blow up anywhere, this probability distribution. This is unnormalized. And then this would give you the probability of finding yourself in these various potentials. So in this situation, you can imagine being in a kind of thermal equilibrium, or where it's dominated by the lowest potential here, and there is some small probability of being in all the other values of the potential. So here, the thing that has most probability is to be in an empty universe at this value of the potential. Okay? It certainly does not describe the universe we live in. So, I mean, you can imagine that minimum value is the currently observed value of the cosmological constant. But this probability peaks in an empty universe with our current value of the cosmological constant. And even if you put anthropic constraints, it would favor Boltzmann brains as opposed to so-called Boltzmann brain. Boltzmann brain would be that there is a quantum fluctuation that makes you think you exist, but you don't really exist. Anyway, so not the universe we see. Now, the potential that we have in string theory is not like this, but contains regions where it asymptotes to 0, right, to maybe supersymmetric vacua, maybe decompactified spaces, and so on. It has also regions where it's negative, right? So these are ADS vacua. These are the ones that we have been we study a lot, the supersymmetric ADS vacua, for example, and so on. So it has a more complicated structure. And in this case, this simple probability distribution even does not seem to make any sense because it would blow up exponentially as we go along these regions. And well, there are some proposals for how to think about probabilities in this type of landscape, but there is, I would say, no generally accepted one. Yeah.
Could you also have something like Anderson localization if your potential is sufficiently random?
Yes, the question was, could you have something like Anderson localization, right? So Anderson localization is a phenomenon in condensed matter where you have a potential, right, and which is random. So, and then you have the typical energy eigenstates are wave functions which are localized and not extended. So if you are in one of those wave functions, you will not, move along x, right? Naively, you would move from one x to another. Perhaps, I think people have discussed this. I don't know precisely what the status is. The physics of, the actual equations for this are different than the ones we have here. So I basically don't know. Yeah. I mean, this problem has these features of the universe expanding, producing more and more space, of producing daughter universes and so on, and that that doesn't have an analog in the Anderson localization. So I don't know that you could make an analogy. But yeah, so one question. Okay. I would say probably this is, well, this I think is a very important problem because we think the potential is like this, and we need to be able to, decide how to pick a state, do we pick a state, that is the state picked for us, and so on. These are all questions that some people are working on them, but there are not many papers, I think, written on this. But it's a good question to keep in mind. So to know the question exists, understand perhaps a little better what the question really is. And if you see in anything that you are studying that there might be a potential for answering this question, then perhaps apply that insight that you got from perhaps studying black holes or bootstrap or amplitudes or anions or whatever you're studying, and try to think how to apply to this problem. Okay, so now I was planning to make some comments about one approach to the sitter, or which is you can call the SCFT. So some ideas around this this acronym. So the first observation is, we would like to describe the sitter, okay? But we made a sign error, and we ended up spending a lot of time in anti-de sitter, right? So the question is, they look very similar, okay? And in fact, there is an interesting analytic continuation that explains many observations, which is we can set equal to I eta, right? And then if we start from this metric, we end up with so after this analytic continuation, so we put this here. So this will give us a metric dz squared plus dx squared over c squared up to this overall minus sign, okay? So the metric of de sitter is can be analytically continued to a metric of minus anti-de sitter, okay? And if you put an overall minus sign in the metric, it's still a solution of Einstein's equations with positive cosmological constant, okay? Okay. So this is useful for some purposes, for explaining some connections between some similarities in the connections between formulas that you compute, because the formulas for the perturbations, for example, are very similar to the ADS formulas. And this analytic continuation kind of explains why it is so similar, because the problems are very similar. This minus sign changes some important signs in some locations, so it's not to be neglected. Now, the closest relationship between what we normally do in ADS and what we do in the sitter, well, perhaps there's something I should mention. So in the sitter, we have a boundary in the future, right? So at eta equal to 0, we have some kind of boundary which is somewhat similar to the boundary of ADS, right? So the natural question is, could there be a conformal field theory on this boundary that computes for us, cosmological observables? So think correlation functions on this boundary. So the dual field theory would, if it exists, it will be a Euclidean field theory, a Euclidean conformal field theory. So the analogy that is somewhat close is between the SCFT and Euclidean ADS CFT. So what is Euclidean ADS CFT? So it's a situation where we have a Euclidean boundary, and then we have a bulk, which is ADS. Okay. And in this type of context, we normally have a statement that the gravity partition, the partition function of the CFT, right, as a function of the boundary metrics. So this is the, let's say in 4 dimensions, this is ADS4. So the 3 boundary and the values of the field on this boundary is computed by a CFT, or perhaps because we have a scalar field, we have some scalar operator deformations, more like a QFT. But let's say a CFT with these properties, with these values. So these are couplings of the CFT, and we have some space-dependent couplings, right? And that's supposed to be equal to the ADS gravity action. So the ADS partition function. So there is a gravity action, and then there is one loop determinant, and then there are further corrections. So the full gravity partition function with these boundary conditions is supposed to be equal to this. And so you could wonder whether there might be a similar statement in the sitter case. And the statement that you would like to make is that, let me use the same formula here, that there is some hypothetical Euclidean CFT at the boundary of the sitter 4, and that this would be equal to the natural conjecture is that this would be the wave functional of the universe as a function of the 3 metric and the values of the scalar field. Okay. So this is a wave functional solution of, let's say, the Wheeler-DeWitt equation, or the wave functional in semi-classical quantization. That would be the leading approximation, which will be, again, we'll have a classical action piece and some other pieces in principle. So it's this wave functional. Now, this wave functional in which state, right? So in principle, when we consider wave functionals in the sitter, we can choose different initial states. So the analogy that this seems fitting is here in the ADS context, we choose a no boundary state. So some state that has no boundary in the past. So we sum over everything with no boundary. So here, a natural state, again, is to choose in the sitter, the so-called no boundary state, so some state where in the past you have some excursion into Euclidean time, and the universe shrinks smoothly. So this is the no boundary state, or Hartle-Hawkins proposal. And this is, okay, here I drew the picture for the sitter, but you could evaluate this on any fluctuating geometry, and you will get some solution of the equations, and you can evaluate this wave function. And it gives you the usual answer. So if you evaluate this for small fluctuations, you get e to the minus, m Planck squared, let's say for gravity fluctuations, k cubed times hk. So the same formula we discussed previously. So integral decay of this expression, okay? A Gaussian wave function with the right sign for the small fluctuations. Now, if we did the same computation in ADS, we would get exactly the same type of formula. So in ADS, the partition function on a metric with small fluctuations in the future, Same thing, but with ADS here, negative cosmological constant. I'm here comparing and constructing the two cases. We would have something which has plus m Planck, m Planck square. So this is the 1/g Newton piece. We usually write it in terms of the radius of ADS, but it's basically the same formula that we had before, k cubed hk. Okay, so we have the same, basically the same thing. We discussed the minus sign and minus the metric, and that's responsible for the minus sign we see here. Okay, I mean you can do the two computations independently, but you can understand the theoretical reason, the theoretical unity between these two things. Now I emphasize this sign because this sign appears also, it's correlated with the sign in the stress tensor correlator, which is the second derivative with respect to hk. So this is in momentum space, let's say, k minus k. The delta hk of this partition function and then set in h equal to 0. What that would give us is this coefficient, right? So it will give us the m squared r squared times k cubed, okay? And this is the momentum space form of a correlator for a 3D CFT. And importantly, it has here this coefficient, which is positive, sometimes called the central charge or CT. Okay, it's much positive and much bigger than 1. So this positivity of this quantity is related to reflection positivity of the Euclidean theory. And it's a property of any Euclidean theory that comes from analytic continuation of a unitary Lorentzian theory, as I think Tom Harman probably discussed. Okay. Now, here if we were to ask what kind of CFT do we get, well, it would be a CFT whose partition function is this. We can calculate the two-point function of the stress tensor in this CFT. It will be given by the same derivatives, and we will have a minus sign. What this is saying is that whatever Euclidean theory we have describing de Sitter, it cannot be the analytic continuation of a unitary theory, right? That does not mean it can be anything, because this Euclidean theory has to be such that the physics that we get in time here should be unitary, right? So that's a constraint. So the constraint is that the bulk physics should be unitary, okay? And that translates into some constraints for the CFT, but we don't have we don't have the complete constraints. So we have some constraints for, let's say, 4-point functions, or constraints for some features or some necessary conditions, but we don't have the general sufficient condition that this Euclidean CFT should obey. Now, of course, we have no examples that give Einstein gravity, so otherwise we would be very excited. But we do have one example that involves a weird theory of gravity called higher spin gravity. So an example by Aninos, Harman, and Strominger. So it's an example where the boundary theory is free and is described by free ghost fields, so scalars that are, fields of spin 0 that are anti-Grassmann variables. And the bulk theory is some version of gravity with fields of all possible spins, 2, 4, 6, etc. Okay, so we don't know whether that's just a coincidence and maybe a simple analytic continuation of the similar thing for ADS, or whether it's one really example and that there might be some other examples that we don't know because we don't have the techniques to find them. Now, I should say that there is one feature that is important in the de Sitter case that makes the de Sitter case a bit different than the ADS case. And that's the fact that in de Sitter we're interested in the wave functional of the values of the fields, right? But eventually we would like to integrate over these values. So we want to calculate probabilities where an expectation values where we integrate. We do a functional integral over the 3 metric and the boundary, right? So we normally have to do this last step, right? And for example, when we discuss the expectation values of the gravity waves, right? we did do this last step of integrating the Gaussian wave function and getting the expectation values. And even if you were interested in the raw probability at some maybe locations or for some processes, you would like to integrate over the regions you do not observe, at the very least. So you always have to do some integral. And once you do this integral, this whole thing becomes more like a theory of gravity in one less dimension, right? So because we are integrating over the metric. And it's a theory of gravity which is a bit similar to the worldsheet in string theory in the sense that this piece will be a conformal field theory. And so it's a theory of gravity which is Weil invariant and so on. And in some cases, there is a very close connection to string theories. So for example, in three-dimensional gravity in the sitter, there were some recent papers on the so-called complex Liouville string, which is the kind of two-dimensional field theories that we would find in the future of three-dimensional de Sitter. Okay. 5 minutes, yeah. Okay. Now there are some for each conceptual candidate of the non-perturbative description of de Sitter. So there are various possibilities for the non-perturbative description of de Sitter. One is the static patch, that you have perhaps some quantum mechanics or some system in the static patch that describes de Sitter. The other is this DSCFT, that's another possibility. And for each of these possibilities, there are objections and counter-objections and so on. For this case, one objection is that we discussed that in a more realistic landscape, we expect de Sitter to decay. So the structure of the future boundary would be more complicated. Now, the counter-objection to that is that this wave function would compute the probability that the state has not yet decayed, right? It would be like an exclusive amplitude where we compute the probability that the state does not decay. And so it will be, as we take the cutoff to infinity, we'll get a smaller and smaller probability. So if that's correct, then DSCFT could be correct, but it would be computing the probability of something that is very small. Okay, it goes to zero. It will be like an exclusive amplitude in, let's say, conformal gauge theory, like n equal to 4 super Yang-Mills. People compute them, but it's not really what's physically most interesting. Of course, if someone really found, even if you could find that, that would be wonderful. So it's not clear. Now, another question about this approach of the DSCFT is what is the de Sitter entropy? So in the static patch point of view, okay, the de Sitter entropy is the total number of states in that dual Hilbert space, right? So that has a clear meaning. It's the starting point for the whole discussion. But here, in this de Sitter point of view, what is the de Sitter entropy from this point of view? What exact property of this conformal field theory? Okay. And is there any conformal field theory that we could imagine that has this finite de Sitter entropy? Okay. So as you see, there are many questions, and so things that potentially some of you will find, and hopefully in the not too distant future. So I think, yeah, this is your time. Thank you.
We have time for a question or two.
So you mentioned one proposal for de Sitter CFTs by Andy and Tom and
Yes.
like higher spin gravity.
Yeah.
But in their proposal, it seems like they didn't use the Hartle-Hawking state as the vacuum, but like some other alpha vacuum. Could you please comment on that?
I thought they had just the standard.
They picked the two like in and out vacuum, but that are related by Bogolini. Well, you could imagine picking different vacua here. Okay, yeah. Now yeah. So when you compute this wave function, right? You could compute it relative. So here the boundary conditions you can put in the future could be
various things, right? In this discussion, I was imagining, for example, a scalar field, and we are just putting fixed boundary conditions, right, for the scalar field. But if you had a massive field, for example, you could imagine considering the out vacuum as and putting, let's say, the Hartle-Hawkins state in the past and the out vacuum in the future. Okay. And then you be computing that. So there are different boundary conditions that would be different definitions of the field theory.
I see, but if it's like odd dimensional, at least if in any dimension, I think if it's out in the future, then it's in the past.
Yeah, that's a special feature of I think of certain dimensionalities. That's true in certain number of dimensions. I don't remember whether it's odd or even, but in one of the two, that's true.
In odd dimensions, in is the same as odd, but in any dimensions, it's like in going to out.
Well.
But yeah, maybe it's.
No, let's discuss that. So, in some special number of dimensions, which I now unfortunately don't remember, which it's half of the dimensions. If you choose the in vacuum, right, then there is no particle creation when you go to the out vacuum. Okay. Yeah. So this perspective of the DSCFD I was discussing is most natural if you focus just on one of the boundaries. Let's say the future boundary. You don't have the two boundaries. Now you could discuss also the two boundaries. In that case, you would have two CFDs, right? And well, you'll have to discuss the interpretation of that, right? Of what the two boundaries of the CTER mean. So here I was taking the perspective that there is one boundary that computes the wave function, another boundary that computes the ket of the wave function, the other one the bra. Now you might say maybe this is a kind of wormhole that connects the bra and the ket. You might have that point of view and try to see whether that's consistent. So that's something people are exploring, for example. But in that Aninos et al. Paper, they discuss just one wave function would be the same as the partition function for the free fields.
Okay, so let's save further questions for the break. This was Juan's last lecture before he inflates away. So let's thank him again for a nice series of talks.
Thank you and best wishes.